Every prompt you send to an AI triggers a physical chain of infrastructure, including servers, cooling systems, and substations. It consumes roughly 10 times the electricity of a standard search. Multiply that by billions of requests a day. In 2024, data centers used 415 terawatt-hours globally. A silent boom is fast becoming one of the largest new sources of electricity demand on Earth, and most grids were never designed for what comes next. This global demand of 415 terawatt-hours translates to a massive physical construction footprint, with the United States alone accounting for 180 terawatt-hours of that total. Across major technological hubs, the abstract concept of the cloud is dissolving into the reality of concrete, steel, and high-voltage transmission lines. Major technology companies are accelerating the construction of massive data campuses, turning digital infrastructure into one of the largest industrial development booms of the century. Hosting these facilities requires vast tracts of land, heavy industrial permits, and most of all, guaranteed access to the electrical grid. As tech giants secure these resources, regional planning offices and utilities are finding themselves at the center of an intense competition. Instead of bidding solely for jobs, municipalities now allocate their long-term power capacity and resources to support a digital economy that grows more physically demanding every day. The physical expansion of these facilities is driven by a fundamental change in how computers process data. Standard internet services primarily retrieve stored information, but generative artificial intelligence must actively synthesize new content for every request. A conventional search engine query consumes roughly 0.3 watt-hours of electricity. By comparison, a single request sent to an artificial intelligence model, like ChatGPT, requires 2.9 watt-hours, representing a 10-fold increase in power consumption. This energy disparity is rooted in the specialized hardware needed for advanced computing. Modern processing chips, such as the NVIDIA Blackwell unit, draw 1,200 watts of electricity each. When deployed together, these high-density server racks can require over 100 kilowatts of continuous power, whereas traditional web hosting racks typically operate on less than 10. Because both model training and live user requests demand uninterrupted computation, artificial intelligence has introduced a massive, continuous baseload requirement to the power grid. Unlike typical internet traffic that fluctuates throughout the day, modern data centers require uninterrupted baseline power. The financial stakes of any disruption are severe. Industry benchmarks show that an unplanned outage costs an average of $7,900 per minute. For 97% of large enterprises, a single hour of downtime exceeds $100,000. To avoid these losses, operators secure firm, continuous power commitments from utilities rather than accepting flexible or interruptible service. This demand is further increased by the physical overhead of the facilities themselves. The average power usage effectiveness, or PUE, for large data centers sits in the mid-ones, typically around 1.47, meaning cooling and infrastructure require nearly half as much energy as the servers themselves. As a result, grid planners cannot treat this sector as a variable load that can be scaled back during peak hours. It represents a permanent, year-round baseline obligation that must be met every single second. This permanent baseline demand is forcing grid operators and utility planners to rapidly revise their long-term growth assumptions. In early 2024, PJM Interconnection raised its annual load growth projection to 2.4%, a sharp increase driven by the unexpected speed of data center construction. Nationwide, Lawrence Berkeley National Laboratory projected that U.S. data center electricity demand could rise to between 325 and 580 terawatt-hours by 2028. The speed of this expansion has exposed a major structural mismatch in timing. High-density computer campuses can be built in 12 to 24 months. The transmission lines and power plants needed to serve them require 3 to 5 years to plan, permit, and construct. This temporal gap leaves utilities struggling to reconcile immediate load additions with long-range infrastructure investments. What once seemed like a manageable, localized load is now altering regional demand curves faster than utilities can adapt. Grid operators are no longer planning for the grid they had. Instead, they are being forced to construct a system designed to meet the immediate, continuous needs of artificial intelligence. Electricity is a finite resource. When a single industrial sector requires vast amounts of continuous power, it begins competing directly with other societal needs. New housing developments, domestic manufacturing plants, and vehicle charging networks. Grid capacity stops looking abundant when one class of customer can absorb the entire growth margin of a region. This shift transforms a technical challenge into a question of fairness. Historically, utilities expanded infrastructure and spread the bill across all ratepayers. Today, regulators are pushing back. Commissions are designing large load tariffs, requiring these massive new digital facilities to fund the specific substations and transmission lines they require. But cost is only part of the conflict. The true bottleneck is physical capacity. When grid connection queues are years long, prioritizing a data campus means delaying a factory or a residential subdivision. Every megawatt allocated has become a choice about regional economic priorities. In Northern Virginia's Loudoun County, the dense concentration of digital infrastructure has reached a tipping point, with 199 operating facilities and another 117 planned. To escape this congested corridor, developers are racing to Texas, where the interconnection queue swelled to 226 gigawatts by late 2025. Yet only 7.5 gigawatts of that capacity have actually connected to the grid. In arid Arizona, the bottleneck shifts from electricity to water, as massive cooling systems lose 80% of their water to evaporation, prompting Maricopa County to implement a conditional moratorium on new permits. Across the Atlantic, Ireland illustrates the absolute limit of this geographic clustering. Data centers consumed over 21% of the nation's metered electricity in 2023, forcing regulators to impose a de facto moratorium on new grid connections through 2028. This global pattern shows that companies consistently cluster where land and power are easiest to secure until regional systems begin to strain under the weight of the digital load. Every time a user submits an AI prompt, a physical reaction cascades across thousands of miles of infrastructure. The request leaves a personal device, traveling over last-mile networks and backbone fiber links to a regional point of presence. From there, it routes directly into a data center gateway, passing through heavy switchgear to reach specialized GPU accelerators. This hardware generates intense heat, requiring continuous water or direct-to-chip liquid cooling loops to prevent thermal failure. To sustain this work, power flows from dedicated substation transformers connected directly to high-voltage transmission corridors. This physical pathway converts digital queries into heavy industrial actions, tying software directly to the land, water, and local electrical grids. For utilities and regional planners, this invisible cloud is actually a highly material sequence of concrete, copper, and constant power flow. The North American Electric Reliability Corporation warns that this mounting demand threatens the structural reliability of entire power grids. Resolving this strain has moved past technical engineering to become a complex coordination problem for policymakers, utilities, planners, and the public. Managing this transition requires a combination of practical levers, transmission upgrades, renewable plus storage procurement, workload scheduling, geographic diversification, large load tariffs, and community benefit agreements. Yet physical infrastructure projects cannot match the speed of software deployment. If current trends continue, data center growth will keep rising faster than grids can absorb, creating a permanent state of grid strain, delayed electrification, and rising consumer costs. The fundamental question is how quickly physical grids can adapt to power this scale of intelligence. Today, the future of digital intelligence depends entirely on physical infrastructure. We are no longer constrained by software, but by the physical limits of our power grids. As demand surges, the ultimate bottleneck for AI is electricity. Share your thoughts on this evolving crisis below. Every crisis begins as a crack, small enough to ignore, until it isn't.